Hello, my name is Joshua Skiba, and this is the loose screws design project for FSC 100, also known as Agrosmart. The individuals on the team are Isaac Benson, Mark Davis, Caitlin Powell, myself, and Jesse Sprangler. In this presentation, we'll briefly go over the introduction of Agrosmart, individual robot design demonstrations, swarm demonstration, the entrepreneurial aspects of our design process, the summary, and references. Stores all around the world have been experiencing food and product shortages due to supply chain and manufacturing issues that have arrived since COVID-19. Farmers and agricultural managers perform the important task of delivering products from a field to household tables and pantries. However, these individuals and the farming industry at large could realize greater production benefits through increased application of automation. That's where we founded Agrosmart. In this presentation, we will demonstrate how fully autonomous robots will help farmers all around the world. You will also see the mechanical design, circuit design, Arduino code, and a demonstration of each robot will be presented. Agrosmart is comprised of 5 robots. First off, the soil testing bot, followed by the tilling bot, seeding and fertilizing bot, compacting bot, and finally the watering bot. I will now turn it over to Isaac Benson to talk about the soil testing bot.
Hi, my name is Isaac Benson with the Loose Screws. This is a demonstration of the Agrosmart soil testing bot for Deliverable 3. The purpose of the soil testing bot is to test the soil's nutrient content and communicate its findings to the Central Management System, or CMS. This data is distributed to the fertilizer bot to tailor the fertilization types and quantities to be applied in each sector of the work area. Key features of the soil testing bot include distance sensors for collision avoidance, a vertically mounted actuator, an NPK sensor, which measures the quantity of nitrogen, phosphorus, and potassium in the soil, and an antenna for wireless communication with the CMS. To build the soil testing bot circuit in Tinkercad, some concessions were made based on component availability. This demonstration circuit uses a servo motor in place of a hydraulic actuator, and a soil moisture sensor is used in place of an NPK sensor. The sensors and servo motor are connected directly to I/O pins on the Arduino board. The 2 gearboxes representing the left and right side drive wheels are connected to the Arduino board through an L293D motor driver IC. While a marketable version of this bot would feature more functional logic, the logic, functions, and code shown here represent a basic feature set. It's also important to note that this demonstration assumes a coordinate path and test pattern have already been determined and the bot is on site and ready to work. The soil testing bot's program begins by requiring input from a human interface to initialize the program. Once the sequence begins, the program iterates through a for loop, which instructs the bot to scan for obstacles and move forward slightly. This loop iterates quickly enough that the motion of the bot appears to be seamless. A major benefit to this approach is that it alternates scanning for obstructions and traveling, thereby minimizing the distance the bot travels between the time it detects an obstacle and the time that it actually stops. When the bot encounters an obstacle, it stops and sends a message to the CMS. A request to acknowledge that the obstacle has been cleared is made. When a human counterpart responds affirmatively that the obstacle is cleared, the bot resumes iterating through the for loop until finally iterating out of the loop. At this point, the soil testing bot stops moving and begins its soil testing sequence. The actuator extends downward into the soil. An NPK sensor measures soil nutrient content. To simulate various NPK sensor readings, this bit of programming uses a series of if statements to determine which numeric range the measurement falls into and reports the measured quantities and interpreted results to the CMS for distribution to the fertilizer bot. The remaining portions of code utilize a series of logic decisions and counters to instruct the bot where to travel, when and in which direction to turn, and when it has reached the end of its predefined test path. Upon reaching the end of its test path, the soil testing bot is instructed to leave the test area and send a test complete message to the CMS, which serves as a cue to the tiller bot that it may begin its sequence. The program then enters an empty for loop in which it iterates indefinitely, crudely simulating going into standby mode. The SoilBot code is represented here in 3 pages. So I'm just going to pause quickly here on to the next page where I'll pause again, and then on to the next page where I'll pause again. Going back to the circuit, we will start the simulation. It starts up, welcome to Agrosmart, where we farm the future. Please type S and press enter. So there were some rainy day scenarios. I wanted to make sure that S, capital S and only S would work. So if we enter a 1, it says try again. If I enter lowercase s, it says try again. Only if I enter a capital S, whoops, Shift S, not Control S, does it allow us to get going. And now it starts, the motors are in action. It's going to stop. The actuator turns, it takes a sensor measurement, 0 units. We'll move the soil sensor. Well, we'll move the sensor value, we'll change it, see where it comes to next. We'll change it again, and we'll watch this response change the next time it takes a measurement. And if we max this sensor out, it'll give us a different response. So as we watch these motors turn, this is designed to turn in place. So when it does make a turn, one motor will go completely negative, the other motor will remain positive. And that will cause the bot to spin in place right here. It's happening. It's moving forward. It'll make another test measurement, and then we'll see it turn in place again, in case you missed it the first time. And then it will continue moving forward. Now, if we cause an obstruction, oh, well, we just found a bug. When we cause an obstruction during the soil testing phase, something strange happens. It's continuously operating, continuously moving. Wow, that's cool. Found a bug. All right, so we got an obstacle. Is the obstacle cleared? I am not going to clear the obstacle, and I'm going to enter garbage. And it's going to iterate through, and it's going to say, try again. Okay, I'm not going to clear the obstacle, and I'm going to say, yeah, sure, I cleared the obstacle. It's going to iterate through, and it's going to say, hey, there's still something in my way. So we're finally going to clear the obstacle, and we're going to say, yes, it's actually clear. And it'll say, okay, thanks, moving on. Okay, there you have it. It will continue to do this until it iterates through all of its turns and makes all of its pre-programmed measurements, at which point it will end and send a message saying that soil testing is complete. Thanks.
Hello, my name is Mark Davis with the Loose Screws. This is a demonstration of the Agrosmart tiller bot for Deliverable 3. The purpose of the tiller bot is to prepare the soil for planting by mixing up the dirt and breaking up clods. Here we see the tiller bot with the front distance sensor, rear distance sensor, Arduino Uno, a servo motor in the rear to control the trim, and 4 gearboxes that control each of the tires. This is the circuit we used for the designing these servo mode or the tiller bot. And to design the code for it, we use this activity diagram. It starts and then goes into a for loop where it checks the rear distance sensor, the front distance sensor. It's going to go forward, right, and then take lefts. And ultimately, it should look something like it goes up, right, right, down, left, left, stop. And then that would be the end of the for loop. Once the for loop's completed, the LED signal will be turned on. A message will be sent saying send fertilizer seeder bot, and it will return to base station. This is the circuit, and if we start the live simulation, we should see that there is an obstruction in the way, and we should see a message down here in the serial monitor. There's an obstruction, please remove, and we bump it out to 124, and we see that the motors start turning on. Currently, the servo motor is raised because the distance between the ground and the distance sensor is not enough. So we'll raise that over 20, and we should see that servo motor go back down. Here on the code, I'd like to just show you the for loop that I used to program this. The farmer can input any amount for rows, however many rows he wants. Also at the bottom, there are 5 functions. One is the check distance. I'll use those for the distance sensors, and the other ones are to control the movements of the bot itself. Once we make it through a full iteration of the for loop, we should see that this red LED turns on. We can see up here, these are at 0. We're currently turning left. And the red light's on, and the send fertilizer seeder bot message has been sent. And this is the tiller bot. Thank you very much.
Hello, my name is Kate Powell. I am presenting the fertilizer seeder bot for my team Loose Screws. This video is for FSE 100 and for the assignment team Deliverable 3. Currently we are looking at a side view of my bot. Towards the back right here we have the seed holders and dispersers. These can be manually adjusted to fit the seed types. Up on top we can see the communication box and the LED. On the inside of the bot, we have the fertilizer valve and container, as well as the Arduino. Looking at the front, we have the distance sensor towards the bottom, and then going underneath the bot is the fertilizer sprayer and the 2 motors, one on the left and one on the right. Going up towards the circuit, you can see the 2 motors right here, the tilt sensor, the distance sensor, and the LED. The tilt sensor was a recent addition. Alright, looking at the code here, we have it in the loop to measure the distance, and if the distance is greater than or equal to 48 inches, the bot will move forward. It will serial print proceeding forward. It will also serial print opening the fertilizer valve. This would be automated in real life, but I do not have the pieces on Tinkercad to make this work right now. If it is less than 48 inches, the bot will stop, and it will serial print path is blocked. Continuing on, we have the tilt sensor. This can be changed based on individual terrains, and it can be changed by the farmer themselves. So here, if the tilt sensor is low, because the output is normally read as low, it will continue on. Otherwise, it will go forward and the LED will light up. It will also print fertilizer seeder bot is tilted beyond the allowed scope. With the distance sensor, the LED will light up as well if the path is blocked. So here, we're going to move this to the side just a little bit. I'm going to move this in some. Okay. Let's start the simulation. We'll pull up the serial monitor. Currently, the seeder bot is tilted beyond scope and the path is blocked, as you can see. So if we fix the path, Let me pull it out to about 54 inches. Give it a moment to process. Distance read, it begins proceeding forward, and the motors are going. Here, you can move it, and in real life this would change. Okay, well, that was my bot. I hope you enjoyed.
Hello, my name is Joshua Skibble with the Loose Screws, and I will be presenting the compactor bot for Agrosmart. This is part of Deliverable 3 for FSC 100. The purpose of the compactor bot is to ensure that the seeds are sowed properly in the soil. Once the compactor bot starts, it will receive a command that the seeder bot has finished and is ready for compacting. The compactor bot will also send a command once finished to the CMS in order for the watering bot to start. For my design, I have a distance sensor here up in the front. I have 2 motors here in yellow. I have inside the comms box, I have Arduino in red, and then I have an LED bulb here to identify CMS sent and received messages. On the back, I have the compactor design with a hinge type system, and in this little box here is housing the servo motor. This is my circuit design for the compactor bot. In my code here on the right, I will start the simulation. Once I start the simulation, you can tell it's below 120 inches. Nothing is running, servo motor is not activated, LED light is not activated, and the motors are not activated. Down here is reading it and is yelling system stop, report to CMS. Now, if I go past that, you can see the motors are engaged, prints begin, and is going forward. Servo motor is engaged and the LED bulb light is on. As far as the activity chart for this bot and how it will work with the code, it will say begin, it'll check CMS for query. If a yes, then the LED will light up. It will then check the distance. If it is not with over 120, then it'll stop, raise the compactor, contact CMS, report to CMS. If it is a yes, then it will go through a sequence that looks something like this. So go forward, turn right, go forward, turn right, go forward for exponential amount of time. Turn left, go forward, turn left, go forward for an exponential amount of time. That's 2 rows. It will then check in the for loop if it equals 9 rows or not. If it does not, then it will go back up and it will continue to do this for 9 rows, which is the simulation that we were talking about. If it is a yes, then the LEDs will turn off, send CMS complete, and raise the compactor. For this design, one of the things I changed was the hinge type system on the back. I just kind of had it laying down flat here, but I figured once it was raising and lowering, it would need to actually raise this up and lower the compactor down for the soil. Additionally, the distance sensor in front, I initially had it up here, but it really wouldn't be able to read any obstructions. So I lowered it down to here so I'd be able to read ground obstructions more properly. This is a compactor bot for Agrosmart. I will now be passing over to Jesse Spangler for the watering bot.
Hello, my name is Jesse Spangler with the Loose Screws, and I'm presenting the water bot for Agrosmart for the Agrosmart project. This is part of the Deliverable 3 for FSC 100. The purpose of the watering bot is to receive commands from the Central Monitoring System, or CMS, and then begin its specified programming. For my bot, it will receive the command that the compactor bot has finished doing its job in compacting the soil and is ready for watering. My water bot here in the 3D model, as you can see, a couple of the changes from the beginning is we have added a command wire that actually allows the communication with the central monitoring system, seen by the black antenna right here. You can see it is a little bit more curved than originally was. We do have the Arduino Uno now included with a green door that can shut and protect Arduino from any type of outdoor external environmental impacts. And then the soil moisture sensor on the bottom of the robot is actually now rounded and can articulate back up and down within the robot to traverse uneven terrain. It does have 3 all-terrain tires, with the front wheel having the ability to swivel back and forth, as seen by the orange disc in there. You do have the distance sensor on the front and the distance sensor on the rear, allowing it to check where it is at currently in the row, and if it needs to begin a new row or if there's an obstacle on the way. The water tank is actually now larger to hold more water and allow for the farmer to refill it less during its operations. And then for the 3 back watering spouts, we do have those little purple servos on there that do open and close depending on how much moisture is in the soil. For the current activity diagram for the Arduino code, it is pretty reiterative, so I will not go over the entire circle back process for every single line for sake of time. But in the beginning, after we start, it asks if the serial input equals begin. And if it does, it continues to check if the serial input equals stop. If it does not equal begin or equal stop, then it will go ahead and print watering complete, notifying CMS to send the next bot. And then it also sets the server to 0 to close all the water valves and continues from the beginning again. If it says begin but does not say stop, then it checks the front and rear distance to see if the path is blocked. If it is, it sets the servo to 0 and continues with the program. If it is not blocked, it checks to see if the distance to the front is at the end of the row, and if so, it says the row is complete, sets the servo to 0, begins the new row, and then keeps checking to see if it has began that new row. If the distance sensor for the front is greater than 12, then it continues on to check and see if the moisture is less than or equal to 200. If it is less than or equal to 200, it waters at max flow, setting the servo to 180, which opens the valve for the water all the way. If it is between 200 and 500, it waters half flow and sets the servo to 90. And then if it's greater than 500, it closes the water valve, setting the servo to 0 and starts the code all over again. Here's the current Arduino code for my watering bot. And then for our Arduino Uno circuit, as you can see, we have our Arduino Uno board and a breadboard, along with the 2 distance sensors on the left, the front being the the bottom sensor, and the back sensor being the top sensor. And here we have a servo. We only did 1 servo for this project. You could add more to indicate the 2 other servos on the actual bot, but currently we're only depicting 1 on here. And then we do have the soil moisture sensor, which will detect the moisture in the soil. Starting the simulation, we can see that there's no issues with starting up, and we can see it says, please enter begin to start. So we will begin the process, or stop to end operation. So we'll begin the process. Begin, you will see the servo open to full max flow. It starts printing that it is watering with max flow. And then we can play with the distance sensors, lowering the front down to less than 12, the rear less than 110. It says the path is blocked, notifies the CMS. If we increase that rear sensor to over 110, it will change that that is actually at the end of its row. It is closing the valve and it's beginning a new row. When we increase the rear sensor, or the front sensor again over 12, and notice that it can continue watering and it reopens the valve to max flow. When the moisture sensor is reading the lowest moisture level in the soil, it will water with max flow. When it's about in the middle between that 200 and 500 range, it waters with half flow and prints watering with half flow. And then again, if the soil is completely moist, it closes the valve, notifies that it is watering, that the water valve is now closed, and continues on. When it is done with its operations, it will receive a stop command from onboard sensors. It will say stop, and then you'll see that it will print that the watering is complete and is notifying the CMS to send the next bot, which at this point, there is no other bot after us. And it says that we can please enter begin to start the bot again, or stop the end of operations, because the bot is completely loopable and it has no end unless you actually power it down completely yourself. Moving on, we will go into the simulation side of our swarm. So for our swarm simulation, we actually did a MATLAB program. We edited the program to depict our robots going up and down rows, as will be seen in a moment. So for our activity map, after start, it sets a planned path for scanning. It then sets a planned path for robots number 2 through 5. So that planned path for scanning is only for robot 1. Robots 2 through 5 will actually follow the path of robot 1, and they are non-scanning paths because they pick up an item and they're basically commanded by, the item is the command from the first robot to the second robot. Then the second robot will command the third robot commands the fourth robot, and so on until all robots have completed their assigned task. So we set the robot start points. Robot start points are automatically pre-programmed into the MATLAB programming. The destination points are also pre-programmed, and that is when to tell the CMS that they are complete with their operation and to send the next robot. Select known obstacles, that is the user input. So if you have an obstacle like maybe a telephone pole in the middle of the field or some other sort of obstacle that you would like to avoid, you can automatically set those obstacles for the robots to avoid. Therefore, those obstacles will not be notified to the farmer to be moved. We then set the set target destination for robot 1. So you will select when you want the robot 1 to go ahead and send to robot 2 when to start. So robot 1 destination will be set towards the end of the map. And then plot robots, known obstacles, and robot 1 target endpoint before it begins the actual code. So this code is actually repetitive on this activity map. So it says, has user selected enter? If so, it continues. If not, it continues to repeat until you select enter on the keyboard for this program. For yes, then it moves robot along scan pathway, avoiding obstacles, and then ask if the robot has sensed the end target. If not, it continues to move around along the pathway until it senses that end target. When it senses that end target, it will then tell robot 2 that it has the item. So the item equals command from central monitoring system, start, continue code to start or continue code execution. So when robot 2 executes the planned path, non-scanning and avoiding obstacles, it will check if it has reached its destination. If it has not reached its destination, it continues with its planned path. And if it has, then it drops the item and notifies that to CMS that it has completed its row and is ready for robot 3 to pick up the item and start again. So robot 3, again, same as robot 2, will pick up the item, scan its path, check if it reached the destination, if not, continue. And if it has, drop the item, notify the CMS for robot 4. This continues iteratively until robot 5 completes their tasking. When robot 5 completes their tasking, it notifies the CMS that the work has been completed on the fields and it ends the program. So that is the coding. So running into the MATLAB simulation, we will start the simulation. So after starting the simulation, it will ask us to select obstacles or points to avoid and press enter when finished. So we will select some random obstacles in the field that we already know are currently there. So we'll hit enter. You can see that there are red circles now indicating those obstacles in the field. It then says select finish point in which robot 1 dispatches the next robot, press enter when finished. So we will select near the end of our farming rows because again, we're going to start from the left and continue right. So we're going to select near the end and we're going to press enter, and that will be depicted by the green circle. So now we have time completed 0. So every time we hit enter, the robot moves up and down the rows. So first robot is now proceeding through the rows, avoids that first object and continues down that second row. So we'll speed this up a little bit and the robot continues going back and forth between the rows. Excuse the flashing of the program. Goes around that third object again, continues. And then towards the end, it detects that it has received that object, notified the CMS, and dispatched robot 2 now. Robot 2 will go to the beginning of the program path and start their program path back and forth. Maneuvering around any obstacles that may be in its way. And then when it gets to the end, you will see it actually flashes and notifies the next robot to start, robot 3 to start its assigned tasking. Robot 3 starts its assigned tasking. And when robot 3 ends, you see it flashes and sends robot 4 out. So robot 4 is now dispatched and it starts compacting the fields, avoiding objects that might be already pre-planned in its way. Avoids that third obstacle again. And then as we get closer to the end here, you will see that the robot 4 notifies CMS with a flash. That robot 5 can go ahead and start watering the fields. Robot 5 then begins watering the fields. It will continue watering these fields and avoiding obstacles until it reaches the end. And you see our time completed is 88%, so it's continuing to increase as we go. And when we end the field, you'll see that that is closer to 100%. And then we do have a few seconds afterwards that it actually sits and makes sure everything is okay and completed. It flashes that it is complete with operation of watering the fields. And we can see that the program will go ahead and count out the rest of the 98, 99, and then finally 100%, and then exit programming. And that is it for our swarm simulation. I'm going to pass it back over to Josh to finish out the entrepreneurial aspects along with the other, the summary and then the references for our project. Thank you.
Entrepreneurial aspects of Agrosmart. Initially, the team and I had the robots be in full-scale farming equipment. However, throughout the design process, the loose screws changed the size to a more manageable, smaller-scale robotic design in Deliverable 2. Throughout the marketplace, there are currently few fully automated robots for farming. In most cases, the robots are either for large and vast amounts of land and cost well above what the average farmer can afford. Majority of the robots are also owned by the farms that currently create them, and they're not available to the public. Agrosmart offers value due to 3 parameters that we put into the project. Availability to all farmers, not limited to one crop type, proposed lower cost than traditional equipment, and the current market robots. Customers' investment opportunity that we're looking for, Agrosmart offers an effective way to cultivate land in an effective manner, enables customers to focus on other variables in their farm/land, and it is cost-effective alternative to what is currently available. In summary, Agrosmart is a fully autonomous agriculture element that brings advanced capabilities to the average farmer. Agrosmart will enable the average farmer and land manager the potential of yielding far more crops per acre than ever before. Throughout this design process, the loose screws learned that brainstorming is the most important part of the design process. Working through multiple design vectors helps the engineer into the proper design space. Teamwork can be hard, but if everybody puts one foot forward and does even work, then the design process is pretty smooth. And finally, working in different time zones and remotely has its challenges, but if everybody works together, we can get it done. What we have done differently, have the team work together versus being decentralized and working remote on different schedules, and have scheduled meetings before the due dates to discuss changes and potential variations to the project. Additionally, these are some of the references that Agrosmart used. I hope you guys like it. Thanks for checking out Agrosmart. Enjoy.